Hello class. Today we're going to start with a bit of a demonstration. I have here just a regular old beaker of water, and here is some salt. Just standard old iodized table salt, sodium chloride. Now if I add this salt to the water, to absolutely no one's surprise, if I were to swirl this, stir it up a little bit, we'll find that this salt will dissolve. There is no particulate matter on the bottom of the beaker, and if I were to let this settle, it would be completely clear afterwards. So in the same vein, if I were to take a beaker of oil and add a little bit of salt to it, let's see what happens. Well, here, the salt will not dissolve at all. Let's give it a little bit of a swirl to try to get it to dissolve. This is just standard old canola oil. So I'm agitating it, getting the oil in contact with the salt, and we see that that's had zero impact, right? The salt has not dissolved whatsoever. It is still sitting on the bottom of my beaker. Why is that? Why is it that in the water it completely dissolves and in the oil it does not? So to understand why salt dissolves in water and not in oil, we first have to look at how is it that ionic compounds dissolve. Now, when we have an ionic compound, keep in mind that our salt particles were joined together by strong ion-ion interactions, strong electrostatic interactions. Good example of this is sodium chloride. Sodium chloride, in the case of the water beaker there, was the solute, and water was the solvent, the thing doing the dissolving. And this is the example I'm going to be using to describe how ionic compounds dissolve. So when dissolved, when an ionic compound is dissolved, the ions in the crystal will separate. And when those ions separate, we call that process dissociation, right? We have to remove it. We have to dissociate those ions from the crystal lattice in order to dissolve them. And once dissolved, here we have what's called the dissociation equation. Now for any ionic compound, once those ions are split up and they are dissolved in the solvent, in this case water, we have this equation. Our magnesium ion is dissolved in water aqueous, and our chloride ions are dissolved in water aqueous as well. What does that 2 represent? What does that 2 represent? Right, that 2 will represent the number of ions that dissociate per formula unit of our ionic compound. Right, it's MgCl2. So for every formula unit, 2 chloride ions dissociate for every 1 magnesium. So how does this actually happen? Well, when a solute is placed into a solvent, the solvent particles completely surround the surface of the solute. So we drop in a big crystal, and what's going to happen? Well, those solvent particles will surround that crystal. Now, in the case of our sodium chloride water example, the polar water molecules orientate themselves around each exposed ion on the crystal surface, on our lattice. And how do they orientate themselves? Well, remember, water is polar. So what part is going to be slightly negative? That's the oxygen. What part is going to be slightly positive? That is the hydrogen. So our slightly negative oxygens will be attracted to the positive sodium ions, whereas our slightly positive hydrogens will be attracted to those chloride ions. So, if the solute is soluble, in the case of sodium chloride, it is soluble in water, the attraction between the solvent molecules and the solute ions gradually increases to the point where it finally exceeds the forces holding the ions into the crystal lattice. So those interactions between your water molecules and those ions that are formed will allow the ion-ion bonds to be overcome so those ions can dissociate and thus dissolve. Now, as a result, these solute ions become completely surrounded by these solvent molecules. And we're going to have a look at that in a second. So here we have our block of solute particles, and we see that there is interactions forming between the solvent and the solute. And here we have our dissolved particles, right? Our particles, our solute, is now surrounded by our solvent with a lot of new interactions having been formed. Here's an animation of it happening, right? As the water molecules come, here we have the green balls are chloride. How do I know they're chloride ions? I don't even need to look up here. I can tell because the hydrogens of water are attracted to them. So if we look again, the blue ball here, notice how the oxygens are associating with the sodium and how the hydrogens are associating with the chlorides. So that is how these substances dissolve, right? Water comes along, it interacts with that ion. This allows the ion-ion bond to be overcome. That ion will now dissociate from the crystal and dissolve. But a big question, why is it that the ions do not reform to make salt? If I took that beaker of salty water and I left it on the counter, let's say I sealed it up so evaporation is not an issue, would that salt just spontaneously ever reform? No. No, it won't. Why will that salt not spontaneously reform? Think about it. Why won't it reform? What happens to those ions now that they've left that crystal lattice, now that they have dissociated? Well, they are prevented from reforming because of what's called the solvation cage. In the case of water, we can replace the word solvation with hydration. And it's this solvation cage or solvation shell that prevents these ions from reforming. Because what's happened now? Look, these ions are now surrounded by water molecules. This sodium ion here is completely surrounded by those slightly negative oxygens of H2O. And these interactions, if we want to reform salt, these interactions would have to be overcome. So the reality is, you do not see the spontaneous reforming of salt because of these solvation cages. In the same vein, this applies to chloride ions as well, where we have these slightly positive hydrogens associated with our chloride ion. So that is why your salt just doesn't reform. Once it's dissolved, it's dissolved. There is a way to get that salt back. How did we make sea salt back in the day? Well, we got rid of the solvent. That's one way, right? We can boil all the water off and be left with our salt. So you can reduce the amount of solvent, but we'll talk about that a lot more when we start talking about solubilities. Alright, so that is how ionic compounds dissolve in a nutshell. Right? You add that salt to water, that crystal gets surrounded by solvent, right? The interactions of your water with those sodium ions and those chloride ions allows the ion-ion bonds to be overcome. Those ions, now that they have dissociated from the crystal lattice, get completely surrounded by H2O, forming a solvation cage that stops them from reforming solid salts. So when we dissolve something, there's going to be bonds, interactions that are being broken, and new interactions that are going to be formed, right? Think about that. In terms of water, why is it liquid at room temperature? Well, it's got those very strong intermolecular forces, those hydrogen-hydrogen bonds. Well, if we wanted to interact with a solute particle, right, our sodium ion or our chloride ion, some of those hydrogen bonds are going to have to be broken. They're going to have to be overcome. That requires energy. In the same vein, the ion-ion bonds are very strong. Those need to be overcome, and that's going to take energy. And in the end, we're going to form new solute-solvent bonds, and that is going to release energy. I shouldn't use the word bond, I should say new interactions, right? We're going to form electrostatic interactions between the slightly negative positive parts of your water and your different ions. So the net change we call heat of solution. Is your solution going to heat up or is it going to cool down? So, when attractive forces between particles is overcome during dissolution, this requires energy. And refresh my memory, I just talked about it. What were the two things that require energy? That is going to be the breaking of solvent-solvent interactions. In the case of water, it's hydrogen bonds. Right? We got to separate those water molecules so they can form new interactions with our solute. And we also have to break those solute-solute interactions in order for those ions to dissociate, to leave that crystal lattice. Now, on the flip side, the new interactions that form between your solute and solvent, that will release energy. So remember, interactions broken takes energy, interactions formed releases energy. Now, your heat of solution is going to be the net change, right? Once we add up all of the energy required and all of the energy released, is it going to produce energy or is it going to take energy? So if more energy is required in the breaking of interactions than is produced by the making of new interactions, this is endothermic, right? If you had an endothermic heat of solution, what is that going to mean? Will my beaker start to get hot or will it start to get cold? It's going to start to get cold, right? It's going to start to get cold. Now on the flip side, if less energy is required in the breaking of interactions than is produced in the making of new interactions, then this is exothermic, right? So if we are generating more energy in the forming of those new interactions than it required to break, then it's exothermic. So our beaker will get hotter as a result. So why was it that the salt didn't dissolve in the oil? Let's go back to that question. Why was it that the salt didn't dissolve in the oil? Well, the answer to that question is water is polar, and anything that can dissolve salt needs to be polar. Why? Why is that? Well, the electrostatic attraction between ions is very strong. That is an extremely strong interaction. And if you had a non-polar solvent, remember, non-polar, what's the dominant intermolecular force? It's LDFs, right? It's London dispersion forces. It's very weak forces. So the interactions that can form between the nonpolar solvent and your ionic compound are very weak. They're not nearly strong enough to cause your ions to dissociate. So that is why, if we look at our water versus our oil, that's why it's completely dissolved in the water, whereas the oil here, you can still see that big clump of salt on the bottom, right? There is no dissolving of this salt that happened in this beaker. Right on. Have a good day, everyone.